Okay, so the AC output of each full bridge inverter is connected in series. Obviously, that is when voltage will add up, so that the voltage waveform obtained is the addition of all the individual inverter outputs. Number of output phases, the line to neutral, if you want to call it like that, or a single phase, basically. In a cascaded multi-level inverter is given by 2 times n plus 1, where n is being the number of DC sources. So a lot of people sometimes, for prototyping, scaling, they use, batteries also. Battery being the purest form of DC source, so you can use that, can also be used as a source. Now, what I want to touch upon is that some modulation techniques, and they were, they're very well established for a cascaded type multi-level inverter. So this topic would be a little bit, not fully covered unless if I had not touched upon these, modulation techniques. Now these techniques are also being, they've already been extended to the diode clamp and flying capacitor ones. But usually from an analysis or to start off with, so those who are starting off with cascaded multi-level inverter is the one that you can start off with. It's easier to understand, and how the voltages add up is much easier to understand. So the first technique, I wouldn't call it a technique. It's actually, the first one is what we call angle control method. It's also very popularly known as SHE, called selective harmonic elimination method. So what you do basically is you select the appropriate firing angles or displacement angles, say A or alpha. And then what you do a Fourier series expansion. And when you do this Fourier series expansion, you then select which harmonics you want to try and eliminate. So what you do a Fourier series expansion, say in our case, unipolar output voltages, and they have this symmetry. So per half cycle expressed as due to symmetry, you do a Fourier. So here you have, say, you get V0 and your BN coefficients. The ANs are absent by virtue of this symmetry and all that. And then with these governing equations, what you would like to do, say you want to eliminate, say, the third and fifth harmonic. So here this N, right? So this N varies, is from 1, 2, 3, and 5. So you put, say, 3 over there, formulate 1, you expand this equation, and just, you don't need to go on and on. Just go for these 3 factors. So you get 1 minus cos 3 alpha 1 plus cos 3 alpha 2 equal to 0, and the fifth one. Now what you do, once you have these 2 basic equations in place, it's an iterative process. What is your purpose? Your purpose is to find values of firing angles alpha 1 and alpha 2. So within a sine waveform, you would like to fire your semiconductor device, say IGBT or MOSFET, between 0 to 90 degrees. That's why you see this alpha 1 is less than alpha 2, etc., alpha k less than pi by 2, where you want to fire. And accordance with this firing angle, you should be able to minimize. So I've taken just one example. You can get better results also. So what you do, taking the initial value of A1, or say alpha 1 equal to 0, then you calculate in an iterative manner until the results are stable. So what we do, you put in the initial values, you put in alpha 1 equal to 0, and thereby if you go in this iterative manner, you will get value of alpha 2, right? So what you keep on doing is you got 0, and then you got alpha 2 is equal to 0.523. So now you do a second iteration and you put value of alpha 2 that you got is equal to 0.52, say 359, again into the same equations, and then you get alpha 1 and alpha 2. And you keep on putting these, and you keep on digging in the same fashion till you see that your values become stable now. So from here, from our third or fourth iteration, you see that the difference is very less. Here you had 0.66229. If I just look at alpha 2, 0.66229, 0.66268, 0.66262, 0.6626. See the amount of accuracy we're just getting after 5 iterations. Similarly, for the value of alpha 1, you're at 0.31084, then 0.31127, 0.31121, 0.31122. So it depends on how many iterations and up to what precision or decimal, after the decimal point, how fine you want to go. The reason for showing you this is that, about 5 iterations, you're pretty good enough. Yeah, we're going into, the 5th digit after the decimal place. Not needed that much. So, about 3-4 iterations is more than good enough. And then when you have your sorry for that. So when you have your power circuit that you actually design, in your controller, you program these values of alpha 1 and alpha 2 for firing. So these were obviously in radian. That's where this formula is. It takes these this omega t, cos omega t things in radian. Then you go into degrees. That's it. Another prominent one. So that was a selective harmonic calculation. At the end, I have a table to show you, basically, and we'll look at that at the end. Another prominent techniques are called, phase shifted multi-carrier one. So multi-level inverter with say M voltage levels would have M-1 triangular carriers. A phase shifted multi-carrier modulation, all the triangular carriers have the same frequency and the same amplitude. So when you look at any waveform, you can change the amplitude, you can change the frequency, or you can change the phase. When we say sine omega t plus phi, so you change that phi, right? So what we do here, we change that phase. So, but there is a phase shift between any two adjacent carriers, which is given by phase of the carrier is equal to 360 degrees divided by M-1. So, right. So that is one. And how that is used then in when we use level shifted multi-carrier technique. So we got SHE, we got phase carrier. So between the firing angles, I can use phase shifted carrier. Either I go for selective harmonic combination, but now these will be some prominent techniques which are established, and they are called level shifted multi-carrier techniques. Will be going into them now. So just like phase shifted modulation and M level, say CHB inverter uses level shifted multi-carrier modulation scheme, which will require M-1 triangular carriers. Again, same frequency, same amplitude. Carriers are vertically inclined or say vertically aligned. Frequency modulation index is given by MF is equal to frequency of the carrier divided by the frequency of the modulation signal, which is the same as that for the phase shifted modulation scheme. And the amplitude modulation is defined, say, one of the specific cases that is shown in the result table was for M is equal to 5, where say Vm caret is the peak amplitude of the modulating wave Vm, and V carrier caret is the peak amplitude. And then you have your, say, modulation index given by peak of the modulating wave divided by the peak of the carrier wave into M-1. So these are those techniques which are prominently established and are in very use. They are called, the first one is called in-phase disposition. Second one is called alternate phase opposite disposition. The last one is called phase opposite disposition. So in phase, so these are all dispositions. So you have, say, one sine going and you have 4 carriers. So here only there you give a DC biasing to them and lift them up, and you see that they are all, say, in phase. There is no phase shift between what? The carriers, the triangle carriers. Hence you get the name in phase disposition. Now when you look at alternate phase opposite disposition, properly known as APOD or APOD. You see the first one, the peak is, the peak is here, say it, and then the one immediately below it, it will have its low end peak. So it's like, you have made one as the peak, and on the other carrier's peak you have, inverted it, like. So they go, and then when you go for the other ones below the zero level, again that same thing is repeating. So you can say, if you look at VR1, VR2, and then say VR2 dash and VCR 1 dash, that is, they are alternating, and hence the name APOD, and that's how the name comes. Then another one, the third one, which they say phase opposite disposition. You see, these two, they are, very similar to what these two ones that we have at the top, and then the other ones, they are in opposite. Their peaks are opposite. So that's how these three prominent techniques are. You have in phase disposition, everything, in phase. Then you have this one, which is called alternate phase, alternate phase opposite disposition, and here you have phase opposite disposition. Very established techniques. And once you have your carriers and sign, what actually then happens is that they are then responsible for generating your gate pulses and all that. So this was just a comparison I have done some time back. So when you do a comparison, the purpose of me of showing you this is that, how these techniques, they are so much close. I mean, and the percentage THD almost very similar. I mean, 2.9, 2.8, 2.9, 2.7. But when you do this type of analysis, you must be very sure that you are keeping all the parameters, ideally the same. I mean, the number of levels have to be the same. Your carrier frequency has to be the same. Your modulating waveform, the peak, the amplitude of that, the frequency of that has to be the same. Then and only then you can do this type of comparison. So this was a very specific case. I've not given all the details of what was the switching frequency and all that. Suggest that you guys can also experiment and try it, and try and generate a similar comparison, and then you will get a more understanding of how each of these inverters work, and how these modulation techniques are implemented and how they work. Pros and cons of multi-level inverter. Obviously we always talk about the advantages why we want to do that. So output waveform, the quality, the output voltage is low distortion. You have a reduced dV by dt stresses on the switches, and thereby also improving the EMC, electromagnetic compatibility, can be minimized. So what happens now, since you have a multi-level, in a traditional way, all the dV by dt that only one switch or two switches were undergoing, that has been reduced, because now you are exposing your switches to a lesser voltage level altogether. And sometimes if you have too much of a high dV by dt, and your switching frequency gets such that sometimes it starts getting into radiated type of emissions, and it can cause EMI EMC problems. So that is one example. Second, common mode voltage. A smaller common mode voltage results because in the stresses of the this is for a particular example. If you have a drive, this will result in stresses of the bearings of a motor being reduced. What is common mode voltage? This goes back to something like common mode noise, where if you have noise traversing on, say, the incoming two lines, say the positive DC rail or negative DC rail, or say of the phase and then the neutral, and then they return back through the common earthing path. So anything which flows through that and causes a voltage, that is called a common mode voltage. That's the reason. It's because it traverses the common path. Other type is, differential, where it traverses on the positive and returns back through the negative, and vice versa. Input current distortion. So now, since you are going in steps, the current that you are drawing from the source will also be with, a lesser distortion, because you have essentially broken up the whole DC link into smaller DC link values. Yeah, so you can, switching frequency you can play with. You can go up with higher frequency. That is now the trend. Generally, lower switching frequency usually means lower switching loss and higher efficiency. But nowadays, again, as I said, higher switching frequency is the trend, because you can go for, ZVS and ZCS type of topologies. So your switching losses are also reduced in that. Higher voltage capacity, the structure can be utilized in high and medium voltage application. That is one of the purposes. So previously what has happened is that, you had a restriction on how much, voltage capacity your power devices would have. So suppose your voltage device can handle only 500 volt. So now you can cascade all those 500 volts, and you can go up to very other high voltage levels that you need as per your design. Low percentage total harmonic distortion and dV by dt. I think we touched upon this throughout the entire core session. The output voltage waveform is composed of voltage levels more than 3, which leads to lower THD, and dV by dt compares to a 2 level one. Yeah, disadvantages, everything has, two sides of a coin. So the more the number of power semiconductor switches, implying more number of gate drive circuits, implying the overall system would be more expensive and complex. More number of switches, more drivers are required. System becomes complex. And another important point is that the reliability also goes down. More number of components you have in a system, any one fails, your system fails. So first you had only, say, 4 components. So any of those 4 would fail, it fails. But now suppose you have 20 components. So the probability of failing goes up, because now you have, say, more components. So the reliability will go down. The capacitor banks insulated sources needed to achieve the voltage steps on the current corresponding DC buses. Yeah, so you have to, you have to have make a separate source for each step you want. Either you will have to increase the number of capacitors, or say those diodes, or say different DC sources for the amount of steps you want. So complexity will increase. So at the end, it's up to from a design perspective. So job opportunities, we have companies which are now looking at, multi-level type of topologies, because of, you don't have to go to, like 11 levels. So 5 levels quite good enough to give them benefit. So you have these companies which are into power electronics side, and so autometers, Meda servo drives, Titagarh wagons. They are into, the railway business. And the railway business, they have, these 3-phase inverters, converters. So these fields are open basically. General Electric, again, GE Transportation is there. Eaton, they're into mobility. Delta Danfoss, very good for drives. ABB, not only for drives, but power electronic converters, especially for power quality improvement when they are using active power compensation techniques. And Alstom is there. Hind Rectifier is there. So a lot of companies, with their R&D, they look at these topologies, and some of them have already put them into use. I mean, you can go through these slides. These are some of the prominent references that we have used for our discussion. Can have them and, go through them for more detailed analysis. 14 references we had taken for this.